Have you ever just stopped and wondered why some things happen? An ice cube melts, a log burns down to ash, but you never, ever see that happen in reverse. What's the secret? What's the rule that dictates this one-way street of change in our universe? Well, today, we're going to pull back the curtain and uncover the hidden laws of spontaneity.
Okay, let's start with something super simple, something you've seen a million times. An ice cube melting. It just happens, right? On its own. We'd call that a spontaneous process. But have you ever been staring at that same puddle of water on a warm countertop and seen it suddenly decide to gather itself back up into a perfect ice cube? Of course not. So what gives? Why does change seem to be a one-way street?
All right, to solve this whole puzzle, our first clue comes from one of the most bedrock rules in all of science, the idea that energy is conserved. It can't be created or destroyed. Now, this is a really powerful starting point, but as you're about to see, it doesn't actually give us the whole picture.
So before we can go any further, we gotta get our terms straight. To keep track of energy, scientists basically draw an imaginary box around what they're looking at. Inside that box, that's the system. It could be our ice cube, a chemical reaction, whatever. And literally everything else in the universe outside that box, that's the surroundings. This simple little division is the absolute key to understanding where the energy is flowing.
This leads us right to the first law of thermodynamics. And hey, don't let the equation scare you, it's really just a simple accounting rule. It just says that the change in the total energy inside our system, which we call internal energy, or U, can only happen in two ways. You can either add or remove heat, which is Q, or you can do work on the system or have the system do work, and that's W. That's it. Energy is conserved, it just moves around and changes form. The key thing to remember here is perspective. Everything, and I mean everything, is from the system's point of view. So, if our ice cube, the system, soaks up heat from the kitchen counter, then Q is positive. The system gained energy. If a gas inside a piston, our new system, expands and pushes up a weight, it's doing work, so its W is negative. It spent some energy. This simple little sign convention is exactly how we track the flow.
Okay, so most chemistry that you and I see happens right out in the open air, where the pressure pretty much stays constant. To make life easier in that really common scenario, we use a concept called enthalpy, which we label with a capital H. Honestly, you can just think of the change in enthalpy, or delta H, as the amount of heat the system either absorbs or gives off. It's our go-to practical tool for measuring that heat flow, Q, that we were just talking about.
So, the first law tells us that energy has a perfectly balanced budget. It never just vanishes, it just gets shuffled around. But this brings us to a huge, glaring problem. If all energy is doing is being traded back and forth, why don't things just happen in reverse? And this, right here, is the core of our mystery. According to the first law, there's absolutely nothing wrong with that puddle of water giving its heat back to the warm air to freeze itself back into an ice cube. The total energy would be perfectly conserved, but it just never happens. The first law tells us nothing about the direction of spontaneity. We are definitely missing a piece of the puzzle. And that missing piece, our second and frankly most important clue, has nothing to do with how much energy there is. It has everything to do with how that energy is spread out. It's all about a fundamental driving force of the universe, the unstoppable march toward disorder. This missing piece is called entropy, and we represent it with the letter S. You can really just think of it as a scientific way to measure messiness, or randomness, or chaos. A brand new, perfectly ordered deck of cards has very low entropy. You shuffle it once, now it has high entropy. It's that simple. And this brings us to the second law of thermodynamics, which is honestly one of the most profound ideas in all of science. It basically says that for any change to happen all on its own, the total entropy of the universe, that's our system plus the surroundings combined, has to go up. Nature doesn't just conserve energy, it is actively, relentlessly working to spread it out to get messier. This is a great way to picture it. Our ice cube, right? Its water molecules are locked into a perfect repeating crystal lattice. That is a state of very low entropy. It's incredibly ordered. A puddle of water is more disordered, and steam is even more so. Think about your room. There's maybe one way for it to be perfectly tidy, but there are millions of ways for it to be messy. Statistically, disordered states are just overwhelmingly more probable. So really, nature is just playing the odds. Okay, so now we have our two major clues. The change in heat, which we call enthalpy, and the change in disorder, which we call entropy. The final step in our investigation is to combine these two ideas into a single, incredibly powerful tool that can predict the direction of pretty much any change.
And here it is, the Gibbs free energy equation. This is the ultimate predictor we have been searching for. It's a beautiful tug of war. On one side, you have delta H. That's the system's drive to give off heat and get to a lower, more stable energy state. And on the other side, you've got T times delta S, which is the relentless drive of the universe to increase its total disorder. This one equation masterfully balances these two competing forces.
And the best part? The rule for using it could not be simpler. Once you've accounted for the change in heat and the change in disorder, if that final number for delta G is negative, the process is spontaneous. It's a green light. It will happen. If delta G is positive, it's non-spontaneous. Ain't gonna happen on its own. And if, by chance, it's exactly zero, the forces are perfectly balanced and the system is at equilibrium.
This table really shows you how that battle between enthalpy and entropy plays out. Look at the top row. If a process releases heat, which is favorable, and it increases disorder, which is also favorable, think of a fire, it's always going to be spontaneous. Both forces are pushing it forward. But now let's look at our melting ice cube at the bottom. It has to absorb heat, right? That's an unfavorable delta H. But it dramatically increases disorder when the solid turns into a liquid, a very favorable delta S. And that T for temperature in the equation is the tiebreaker. As the temperature goes up, that entropy term gets more and more powerful, until it finally overwhelms the enthalpy term, delta G flips to negative, and poof, the ice melts. That's the secret right there. So we've cracked the case of the melting ice cube. But this idea is so much bigger than that. Understanding Gibbs free energy, it's like having a crystal ball for the entire world of chemistry. With this one amazing tool, scientists and engineers can predict if a reaction is even possible before they start. They can calculate the exact temperature they need to hit to make a reaction go. It's absolutely fundamental for designing everything from new medicines to the fertilizers that grow our food, and even for understanding the incredibly complex chemical reactions that are happening inside our own bodies that keep us alive. When it all comes down to it, it's this single, powerful equation that acts as the final judge. By perfectly balancing that deep-seated drive for lower energy against the relentless universal push for higher disorder, it gives us the definitive go or no-go signal for any process in the universe.
And that leaves us with one final, much bigger question. The second law says that for every single thing that happens, the total disorder of the universe goes up. So if every spontaneous process, from a star exploding to an ice cube melting, is pushing the universe toward a messier and more spread out state, what happens when it finally gets there? What does that end state look like? Something to think about.